All right, thank you very much. It's always nice to come back to visit. So I'm going to be telling you about two papers that I finished this summer on three-dimensional gravity. To set the stage, so dilaton gravity in AdS2 is holographically dual to random matrix theory. And this suggests that pure gravity in AdS3 is holographically dual to some kind of random two-dimensional conformal field theory. But both sides of this equation, if it's true, need to be defined. Pure gravity means schematically a theory that's defined by integrating over just the metric. So the metric is the only dynamical variable, and also summing over topologies. On the CFT side, well, there are several proposals to define what we mean by a random two-dimensional conformal field theory. There's one that's based on the bootstrap and taking some input like the spectrum and some leading OP coefficients and plugging that into the bootstrap to define properties of the random CFT. There are other methods based on random matrix theory together with spectral analysis, tensor models. All these proposals are incomplete in that there isn't a systematic, unambiguous way of calculating all of the observables of the random CFT. But whatever the definition is, well, certainly certain things can be calculated. And whatever the definition is, the observables of a random CFT, the basic observables are the statistics of the spectral density and the OP coefficients of the ensemble of CFTs. The spectral densities are these rows, and the OP coefficients are the Cs, and these are the properties of the ensemble. In this talk, I'll focus on the bulk, the gravity side. I won't have anything new to say about the interpretation in the dual CFT or how to fully define the random CFT. I'm going to focus on how we calculate these path integrals that are dual to the statistics of the OP coefficients. So the leading term in the calculation of these statistics is a two-boundary wormhole. This is the Madisena-Maus wormhole. And this leading term produces Gaussian statistics. So you have a wormhole with two asymptotic AdS boundaries and three particles going across. Each boundary is an insertion of the OB coefficient. And when you calculate that amplitude, which you can do in the ordinary metric formulation of three-dimensional gravity, you find that the coefficient is this function C0. And C0 is a known function that's related to the structure constants of Liouville CFT, and it could also be extracted from the conformal bootstrap, and it matches this gravity calculation of the two-boundary wormhole. I'm going to parameterize conformal weights in the standard Liouville way. So conformal weights are parameterized by P, and when P is a real number, which for most of the talk, P will be a real number. Then this corresponds in 3D gravity to a state that's over the black hole threshold, or to a normalizable state in Liouville. It's convenient to define normalized OP coefficients by dividing out by the variance C0. So instead of using little c, which is the OP coefficient, I use big C, which is the normalized OP coefficient as unit variance. This is just the leading term, and when you sum over topologies and incorporate the subleading contributions, this should produce for you non-Gaussian corrections. The non-Gaussian corrections are hard to calculate in the metric formalism. That is, by actually writing down the geometries and trying to do the path integral over metrics. A couple of very special ones we were able to calculate the metric formalism, but the state of the art for how to do this now, which is much easier, is to use the Virasoro TQFT that was introduced a couple of years ago. So this is a TQFT that's related to SL2 Archer and Simon's theory. And what it gives you, it translates the bulk calculations in 3D gravity, these TQFT calculations, and provides a set of simple diagrammatic rules to calculate any of these wormhole amplitudes. And you can then use that to calculate the contribution to these statistics, the moments of the OP statistics coming from any wormhole, so coming from any particular topology in the bowl. The leading, or a couple of the statistics, for example, the Gaussian term in the language of Virasoro TQFT, the Gaussian term is calculated by this graph. So remember, I normalized the OP statistics to have unit variance, and that's why this amplitude is equal to 1. In a Virasoro TQFT graph, you have a trivalent graph. Each vertex corresponds to an insertion of the OP coefficient. So 2 OP coefficients is 2 vertices. In the gravity interpretation, each of these is an asymptotic boundary. And then there's this network of Wilson lines. The Wilson lines are labeled by conformal weights. So each of these P's is labeling some conformal weight, which in our case is going to be either a black hole or a state above the black hole threshold, just some prime area above C-1/24 in the dual CFT. I'm normalizing things a little bit differently than most of the literature in Virasoro TQFT, but that's going to be convenient as we go forward. The other important one, another important one for our purposes, is the leading non-Gauss, or one of the leading non-Gaussianities in the ensemble. This one is the connected 4-point function. So it's a contribution to the connected connected 4-point function of OP coefficient C, which each one of these corresponds to a vertex in the graph. And the graph is this tetrahedron. This can be calculated in Virasoro TQFT, and the result is the Virasoro 6J symbol. So the 6J symbol is this quantity in braces. It's the overlap of an S-channel conformal block with a T-channel conformal block. So you can think of this, well, up to normalization, this is the fusion kernel that takes you a conformal block from one channel to the other. And the statistics, since these are calculated in gravity, the statistics are given by these Virasoro T. So the gravity corresponds to 2 copies of Virasoro TQFT. That's why this is squared. So this statistics is the 6J symbol squared. So this gave a much more powerful way of calculating these wormhole amplitudes, but there are many interesting questions that remain. Can we calculate the path integral by gluing together simple geometric building blocks? Something like what's done, perhaps similar to what's done in 2-dimensional gravity, where you can use topological recursion to glue together and build up more complicated topologies, or maybe it's something different in 3 dimensions. What are the semiclassical geometries in these Virasoro TQFT calculations? So although Virasoro TQFT gives you a way of calculating the answer, which is supposed to be the same as the gravity answer, it doesn't actually give you the geometry. And in fact, it can be difficult to tell what geometry you're actually working with when you do a calculation in Virasoro TQFT. There are some cases where it's not clear whether it has boundaries or not. Even for this case of the tetrahedron graph, we didn't know what the semiclassical geometry was for that calculation. A couple of harder questions, perhaps. What's the path integral on off-shell topologies? By off-shell, I mean on topologies that don't admit a hyperbolic metric, so that you can't express it as an expansion around a saddle point. And then finally, what is the sum over topologies? Ultimately, we need to understand how they do the sum. So in this talk, I'm going to give an answer to the first 2 questions, how to understand the path integral by gluing together simpler geometric building blocks. And the idea is to calculate the path integral of 3D gravity from a generalized triangulation. And I'll explain what that is. In the math literature on hyperbolic 3 manifolds, especially work of Thurston, it's the so a key tool there is using triangulations, decomposing three manifolds into tetrahedra. And we're gonna use some of that technology, and some of the things that we'll do in the quantum case will reduce to things that you can find Thurston did in hyperbolic geometry. Along the way, we'll also develop a formalism and interpretation for gravitational path integrals on finite spacetime regions. I'll explain how that's connected. Okay. Questions so far? Okay, so I want to begin by setting up the problem of gravity on a finite region. And when I say finite, I mean compact. Okay, so we're doing the path integral, and we're summing over metrics. So we start with a compact region, and the fact that it's finite means the semi-classical saddles on these compact topology, on these compact manifolds, will have finite volume. So the goal is to formulate the gravity path integral 3 dimensions on a compact region with consistent boundary conditions. Picture maybe looks something like this. This is some complicated free manifold M. I've drawn it as just a blob, but there could be some arbitrarily complicated topology inside there. And then the boundary in this case is the union of 2 Riemann surfaces, one genus 2 and one genus 3. And we want to understand what boundary conditions we can impose on a manifold like this and do the pathing. What we're going to do is we're going to choose a Pants decomposition on each of these boundary components. So we'll choose a Pants decomposition on each Riemann surface here, and then fix the lengths or the dihedral angles of the geodesics of the curves in that Pants decomposition. Okay. When you impose boundary conditions like this, whichever one you pick, whether you fix the lengths or you fix the angles, the saddle points that we end up with, and I'll explain the action in a second, but the saddle points that you get when you impose these boundary conditions have a boundary which is called a pleated surface. So a pleated surface is a two-dimensional surface with corners on geodesics. So that's what this is showing a pleated surface locally. There are two hyperplanes meeting. Each of them has extrinsic curvature 0. And this boundary has extrinsic curvature 0 everywhere except on this collection of geodesics where we impose the boundary conditions. Where we impose the boundary conditions, either fixing the length or the dihedral angle psi on this blue curve, that gets bent into a corner. And so I didn't try to draw the corners on this manifold, but you have to imagine that when you solve the equations of motion with these boundary conditions, each of these blue curves, there's a corner where and how it's embedded. So this embedding of this is now embedding hyperbolic surfaces into H3. This embedding of hyperbolic surfaces into H3 with corners on geodesics is a pleated surface, which is an idea that was for a construction that was used heavily by Thurston.
With KIJ.
That's the extrinsic curvature of this boundary as embedded in the 3 manifold, which is over here.
Mostly those geodesics sitting at the minimal length location, and you're imposing those conditions with chemical potentials. That's sort of the idea.
I'll give how we actually impose that conditions now. So if you want to fix the geodesic lengths, then one way of doing that is just to choose Dirichlet boundary conditions, where you fix the metric to be the hyperbolic metric with the lengths that you like. So you need to have a well-defined variational principle. And the right action for that choice of boundary conditions is just the usual one. So there's the bulk term with the cosmological constant. There's the GHY term. There's no counter term because all boundaries are finite. Mathematically, this is specifying some point in technicolor space for each component of the boundary. the alternative is to fix dihedral angles. The way of fixing dihedral angles is to add chemical potentials. So here it's just the regular action, and then you add chemical potential psi I for each of these boundary curves, gamma I. So this is sort of like adding a defect, but it's a defect that's on the boundary of your compact region. We're not actually adding a defect. It's just a way of choosing. We're not adding any extra particle or anything. It's just a way of specifying the boundary condition. And adding this chemical potential will cause this to pick up a delta function in the extrinsic curvature, which fixes the dihedral angle to be psi I.
So when you do this, do you end up with boundaries that are not constant curvature intrinsically? Because fixing geodesic lengths, you said, is like fixing constant curvature metric on boundary.
So what you do is you impose free boundary conditions on the metric elsewhere, and on the solutions they end up being hyperbolic. They end up being hyperbolic away from the corners. So yeah. In the first case, this was picking a point in tabular space. In the second case, this fixing dihedral angles, this also has a mathematical description. So this is called the bending measure, which is fits into the work of Thurston again, this thing that we're specifying is called a measured geodesic lamination. The case that I'm talking about is a restricted type of geodesic lamination. So the ones that Thurston talked about are much more complicated, but I'm restricting to real lengths, rational laminations, which means laminations that came from a pair of pants, much more complicated, like infinitely curly queuing geodesics where you impose a bending measure. And I'm sticking to statistics of scalar operators in the CFT. There has been some progress in 3D gravity in the classical case by Schlenker on understanding the more general case, including the spin, but I'm just going to stick to scalars. So that's the boundary condition that we're talking about. This is a little bit unfamiliar. This is not usually the path integral that we do in AdS3 but gravity with finite boundaries is actually in many ways simpler than gravity with asymptotic boundaries. With the usual asymptotic AdS boundary conditions, the path integral Z of j depends on an infinite amount of boundary data. You have to specify the source, which is the whole function, everywhere on the boundary. This is true even in 3D gravity, where you have boundary gravitons to worry about near infinity. Observables with the ordinary asymptotic AdS boundary conditions are correlation functions that depend on kinematics and can be expressed as sums over conformal blocks. So these are complicated objects. By contrast, in 3D pure gravity with finite boundaries, the boundary conditions are just a finite list of numbers because it's just for a genus G surface, 6G minus 6 real numbers. Since I'm actually picking real lengths as opposed to complex lengths, it's 3G minus 3 for the case that we're talking about. And the observables are OP statistics. They're these observables of the ensemble. There are no kinematics, there are no conformal blocks. These path integrals just directly calculate the OP statistics of the underlying ensemble. From the ensemble point of view, maybe these asymptotic boundaries are sort of a distraction, and then we can put them back. We can do the calculations on the finite, on the compact manifold, and then we can put back the asymptotic boundaries later if we choose. Similar to decomposing JT gravity into trumpets and inside region.
Obvious why this would give us the OP statistics.
I don't think it's obvious, but I don't think it's obvious, but that's basically the content of the slide. So maybe ask me again if I haven't covered it. So yeah,
Is it clear that if you add matter, so if the theory is no longer topological?
Yeah.
That you can still do this finite boundary conditions in a consistent way?
I wouldn't say that's clear, no. I think if they're just defect particles, like heavy defect particles, then I think it's clear. But if you want to do quantum fields or something, then I haven't thought about that. Well, I think it's still possible for reasons that will be on like 1 or 2 slides when I talk about the same construction in higher dimensions, because adding matter in 3D is kind of like higher dimensions. So the dictionary in the case of finite boundaries is simply that these normalized OB statistics, that is, first we normalize so the variance is 1, and then we calculate the statistics of these normalized OB coefficients is equal to, these are equal computed by the gravity path integral with fixed length boundary conditions.
I'm several slides behind. When you have these statistics, what are you averaging over and what weight?
Well, what we're averaging, I would say the definition of the ensemble, averaging over. You can think of the ensemble as being the thing that gives you these moments, that defines the ensemble. So we don't know what we're averaging over because we don't know the dual CFT, but we can compute those statistics from the bulk and learn about the ensemble.
So you have not yet defined the CFT with some parameters if you're going to average over these parameters.
No, in fact, we don't know how to do that. We don't have to do that.
So you're defining the ensemble from the 3D gravity. So the idea,
Yeah, or at least calculating its observable. We're calculating the observable, the moments of the ensemble from the bulk. And then we're hoping that in the future, someone will come along and tell us how that was supposed to
But
be
then in
defined.
what sense do you have a correspondence where you define the left-hand side as a result of the right-hand side?
So there is a partial definition. There are ways to calculate also on the right-hand side, just incomplete. So,
The left-hand
well, but before it was on the right, yeah. There are ways to calculate in the CFT, but there is not a complete way to calculate. So there's the ways to calculate in the CFT, I won't talk about in this talk, but there's a bootstrap method where you assume that the CFT has an identity operator and a large central charge C. And then you use the bootstrap, you plug that into the conformal bootstrap, and you can kind of order by order learn about some of the moments of the OB coefficients. Whether you can do that systematically to all orders is not clear. But there have been some that have been checked that way, and those agree with the bulk calculations in 3D gravity.
I've already interrupted you. The CFT that you have in mind, is it this Liouville CFT or?
No, it's not, it's definitely not Liouville theory. It's something like a holographic CFT or some average over holographic CFTs. So it has a normalizable vacuum and it has a Carty density of states above the black hole threshold.
But the spin 0 sector still has the DOZZ 3-point function.
Yes, but with a different density of states. It's the normalizations in the DOZZ 3-point function are different in 3D gravity as compared to Liouville. So like the 4-point functions are different. The 4-point functions
Both satisfy the crossing.
both satisfy crossing, but there's 2 different 4-point functions.
The density of state?
But
The density of state.
it's Carty
Okay.
in this it's Carty. Liouville it's flat.
That's just a renormalization, a redefinition of spectrum. Anyway, we can talk about it later. It's the same 4-point function.
No, I think the invariant way of saying it is that the 4-point functions are different.
It is very well.
No, they are different because the Liouville 4-point function has no identity term, whereas the gravity 4-point function is approximately equal to the identity one.
That's just a fusion matrix.
No, because that fusion matrix, If you do the fusion transformation, you don't get the Liouville 4-point function. There's the factors of row 0, the density of states showing up there are different.
That's just a normalization of your operators, but anyway, we can discuss.
Okay. Yeah. I think as a function of the cross ratios, I would say they're just totally different functions. Okay, but we could talk about it. If we take 2 points, if we take 2 points close together, the singularity is either z to the minus 2 delta or it's not. And in gravity, it's z to the minus 2 delta. In Liouville, it's more like z to the 1.
Yeah, but that's precisely the normalization. Because that's only for the identity, if the two operators are identical.
Okay, let's talk about it. Yeah. Okay, so where was I? Okay, so this is the statement of the dictionary. In terms of the connection to Virasoro TQFT, this is saying that the fixed length gravitational path integral is the Virasoro TQFT amplitude squared. So how do we confirm this? Well, this is really just a restating of the usual AdS3 dictionary. And to confirm it, what you should do is you should take this core region, this compact manifold M that we're talking about with fixed length boundary conditions, and glue back the asymptotic boundaries. At that point, it starts to matter what observable you're calculating. You could calculate like a higher genus partition function or correlation function, or you could just calculate the statistics. And the way you can do that is by taking your core and gluing it to some asymptotic flares. What I have in mind here is each boundary has 3 heavy operators inserted. There's a way of dealing with heavy operator insertions that was understood by Pedro Vieira and Rob Myers and Jacob Avagian and collaborators. And what happens is each of these flares puts back in a factor of C0. And so this thing is the normalized OP statistics. And then each of these flares put back the factors of C0 so that you get the ordinary OP statistics.
Sorry, can you explain again what these things are that you touch? Systems. You call flares, I don't understand geometrically what they.
It's a bit hard to, I don't want to get too far afield and explain exactly how it works, but I'll give the quick version. So that this is a boundary with 3 heavy operators inserted. And you can think about that as a branched cover of something with this topology of this pair of pants here. You have to construct a branch cover with an infinite number of sheets, and then you can interpret that as having 3 operators inserted on the back. So this is the construction of Vieira and collaborators. But if you want to have a more ordinary kind of observable to glue to, you can take this same core and you can glue it into, say, some higher genus partition function on the boundary. If you do it that way, then the extra stuff that you put at the boundary, that will account for the characters or the conformal blocks that you need to get that observable to work correctly. So I've described this in 3-dimensional gravity. I think that similar boundary conditions exist in higher dimensions. They certainly exist semi-classically, where you would fix the areas or dihedral angles of codimension 2 extremal surfaces on the boundary. So instead of fixing the geodesic lengths, you fix the areas of extremal surfaces. The fixed angle action is similar to what we had in 3 dimensions. You just add some boundary defects to the standard gravity action. These fixed area boundary conditions have been discussed before. The only difference here I'm pointing out is that I think you can do this on compact manifolds, not just on the non-compact manifolds that people have discussed in the context of fixed area boundary conditions, but also on compact manifolds. And that this is the natural starting point to study the statistics of black hole operators in higher dimensions. I expect, but haven't shown and don't have any calculable examples, but if we extrapolate from 3 dimensions, my guess would be that this is a well-defined boundary condition for quantum gravity on a compact region. And furthermore, I would guess that there are classical saddles if the bulk topology or the choice of these boundary surfaces is sufficiently complicated. To explain this latter statement, let's go back to 3 dimensions for a minute. If you have a handle body core and you try to impose fixed length boundary conditions on some simple curves like these, you won't find a saddle. At least not a saddle with non-zero volume. But if you pick your enhanced decomposition to look like this, then you will find a saddle. And in fact, this is an example that I'll discuss later in the talk where we know exactly what is the classical saddle of those boundary conditions. So you have to sort of choose you have to choose your cycles to be complicated enough in order to be able to support classical geometry.
Yeah, so you're doing the boundary conditions of the potential, so it's like switching between microcanonical and canonical. And is how I'm imagining it at that. So what's the standard deviation for A? Or do you know what the standard deviation for A would be in this picture? Since you're not fixing A exactly, you're like working in this different ensemble and then you take the potential to be big, so then it's like sharply peaked.
This is a fixed angle. Yeah, this isn't really a fixed area boundary condition. This is a fixed angle boundary condition, and then you would have to Legendre transform back.
Yeah.
To get the fixed area.
But then I'm saying,
But you're asking what the variance is of the area. I don't know the answer, but I think that's been discussed by in papers of Don Merrill, Shidong, and collaborators on fixed area boundary conditions, but I don't remember what the.
you know what it is for L in terms of the CFD2 case, since you're
No.
working at fixed L, okay.
No, I don't. In higher dimensions, it seems very difficult to find these saddle points explicitly. But I think that the dictionary is.
Yeah, question, is there any solution that we do know that has an asymptotic boundary? For example, with boundary at S1 cross sigma G or something like that, can you use that saddle that you do know to construct one at finite? Or you always have to start from scratch?
You mean in 3 dimensions?
You know, so that's what I was talking about was the boundary, so that would be dimensional.
I don't know of one. I don't know of a single example of this
Okay.
in higher dimensions. So the answer is that I don't. So that was the statement of the dictionary. This is useful for actually finding the classical geometries. Okay, so now you can actually find the geometries and you can calculate the statistics classically. A convenient way of describing these classical geometries in 3 dimensions is that the classical geometry of the core can be constructed using this generalized triangulation, which is a decomposition into generalized hyperbolic tetrahedra. So these generalized hyperbolic tetrahedra look like this. They're tetrahedra where some of the vertices have been chopped off. They can be described as polyhedron embedding space, the embedding space where each n and de Sitter live, but where some of the vertices are allowed to go beyond, are allowed to sit outside, past the conformal boundary of AdS. So when you go to embedding space, it's natural to think about hyperbolic space and de Sitter all living together. So this is a picture that you can get from embedding space, where the hyperbolic space is inside the ball is the conformal boundary, and then there's a de Sitter living outside. And so this is a de Sitter light cone that's shooting onto the future. The sphere is the future conformal boundary of de Sitter. They naturally come together. So in this way of thinking about it, the finite vertices live in hyperbolic space. There can be ideal vertices that live on the conformal boundary, and there can be these hyperideal vertices that live on the de Sitter part of embedding space. To turn this into a polyhedron that just an ordinary polyhedron in hyperbolic space, you then truncate the hyperideal vertices. The way you do that is following this picture, you shine the light cone and then you chop it off here. So the point that this is using is that a point, what this is using is that a point in de Sitter defines the geodesic hyperplane in AdS. That's where you chop it off. When you do this, what you end up with are these truncated faces meet their neighbors orthogonally. That's going to be important because that allows you to glue these shapes together and get smooth.
But where did the sitter come from? I think.
Maybe I can draw a picture. If I draw this over here, people see it? So in embedding space, it's say we're doing, let's do the two-dimensional case, because then I can draw the picture. So this is three-dimensional Minkowski, and this is H2, embedding space. And DS2 is this hyperboloid out here. And you can think about this as being a projective space and project it onto. You can think about this as being projective space, where you're talking about the space of real lines through the origin, and then project that back onto this plane at x0 equals 1. And that's what I've done in that picture. So when you project H2 onto that plane, you get the unit ball. When you take de Sitter and project it onto that plane, you get the outside of the unit ball. And then you have some way of thinking about them all as living in the same space. In AdS2, this is called kinematic space. But in higher dimensions, instead of getting geodesics, they're geodesic hyperplanes. So then you can glue these together to find the geometries. For example, this non-Gaussianity that we mentioned earlier for the tetrahedron graph translates geometrically. You should look for geometry that has fixed length boundary conditions, and the classical geometry in this case turns out to be some finite volume genus 3 handle body built by gluing together two of these generalized tetrahedron. So this is an on-shell geometry that you can describe by gluing together these two tetrahedra. I'm not going to go through the details of that. I just wanted to mention it and point out that you can do these calculations semi-classically. So the classical action on this geometry does agree with the Virasoro 6J symbol. But the reason I don't want to go into the details is that that calculation is sort of messy and long, because the volume of this thing is really complicated. It's some sum of 16 dialogues or something. But it turns out there's a much nicer, more general and exact way to understand the decomposition into tetrahedra that happens in this example and in other examples. And that is by going to fixed angle boundary conditions. So if in this connection to Virasoro TQFT, the natural thing was a fixed length boundary condition. But now I'm going to change gears and in the rest of the talk discuss the fixed angle boundary condition. It turns out that that gives us a very natural way of understanding these decompositions of generalized tetrahedra. So that's where we're going now. Yeah.
So to get the agreement, you don't have to do the determinant around the classical solution, just the action.
No, you have to do the whole thing. I've only checked the classical action semi-classically, but using this other formalism that we're going to turn to now, you get an exact agreement to all orders of perturbation. Okay, so that brings me to the next part, the conformal Turaev-Viro theory. So conformal Turaev-Viro theory, I'll refer to as CTV, is a topological theory that assigns amplitudes to trivalent graphs. So it's similar to Virasoro TQFT. In fact, we're going to see it as a dual formulation, Virasoro TQFT. We'll see that it's also equivalent to 3D gravity on fixed topology. But for now, I don't want to talk about gravity. I'm going to defer all gravity to the last part, and I'll just describe this as TQFT without any reference to gravity. So consider a trivalent graph gamma embedded in some closed three manifold ME with edges labeled by conformal weights P. Next, we choose a triangulation T that decomposes this graph embedded in three manifold into tetrahedron. This triangulation, this is just a just ordinary ordinary tetrahedra at this point, generalized tetrahedra. Just choose a triangulation.
Graph is supposed to consist of edges of the tetrahedron or something? What does gamma have to do with the tetrahedron?
So gamma is a subset of edges of the triangulation. There are edges of the triangulation that belong to the graph. Those we'll call external edges. And generally, you have to also add other edges, and those are called internal edges. Now, I'm going to define the amplitude. First, to each tetrahedron, we assign a Virasoro 6J symbol. So I've given the skeleton of the tetrahedron, and then you can assign the 6J symbol. This is not quite the same as the Virasoro TQFT amplitude for that tetrahedron. In fact, the rows are swapped. Geometrically, this corresponds to dualizing the tetrahedron. But the important point is just that it's not the same. And now we can define the amplitude. So the CTV amplitude is defined like this. You assign a Virasoro 6J symbol to each tetrahedron. So you weight it, product of these 6J symbols, and then you integrate over the conformal weights on the internal edges with the Carty density of states. The Carty density of states is this rho 0. So that's exponentially large that agrees with the density of states of the BTC black hole. So this is the definition of the CTV amplitude.
The range of beams from 0 to infinity.
Yes.
And does this converge?
Not always. So now it's not obvious at all, and the answer is not always, but there's a conjecture for when it converges. So the definition of CTV is the natural generalization of standard Turaev-Viro theory to the Virasoro case. So there's a topological theory, the Turaev-Viro theory that this is based on, and basically I've replaced it with the 6J symbol of Virasoro and the Carty density of states instead of a discrete sum. There's an important difference in CTV, which is that the total number of states is infinite. So if we integrate against Carty, we just get infinity. And this introduces some key differences.
The 6J symbol, if you have a continuous spectrum, is by definition, it depends on the density of states.
Well, it's normalization. Its normalization depends on how. Definition depends on the density of states.
Yeah, because you're right. This thing is a linear combination of others. So it's one thing even when related to an interval. You have to pick a measure on the right hand side.
Right.
And you specify the measure independently of the 6J. You must have had some measure in mind by the 6J.
I think probably this is the only, I did say it that way, but I think this is the only consistent choice. So that measure comes hand in hand with that 6J.
It's the same measure that was used.
Yeah, yeah.
That's how it is.
So one important difference is that it's not obvious that this formula made any sense. So it's not obvious the definition of the CTV amplitude made sense. But in order for this to make sense, it should be finite and it should be independent of the triangulation.
Also to know that integral is of all the real values of P.
It's over real P. Yeah.
So in terms of, again, conformal weights, it's the high energy part.
Yeah, the black holes part. Yeah.
Sorry, but then you said this is a different measure. You mentioned earlier two different measures. One corresponds to conformal field theory study. There's the identity.
Yeah.
And I think the other one is the one that appears in the middle.
For the purposes of, say, like calculating a 4-point function where you sum over internal states, there's two different measures you would use. Yeah.
And the 6J symbol is for one.
And the 6J symbol is for the gravity one, where the measure is Carty. I don't think there's another one that one could use for Liouville. I think this.
Here you do not integrate over imaginary, you integrate only over real.
Yeah, same here.
Then it does not include the identity.
Yeah, this integral does not include the identity.
But the Cardi measure does include.
Well, the Cardi, by Cardi measure, I just mean the Cardi measure on the real P, the heavy space.
So the 6J is the ST overlap with respect to the Cardi density.
You mean by with respect to the Cardi density?
Well, maybe I'll ask later.
I think he's asking the same question I asked.
Yeah, it's the same question I made.
And it's closely related to Hartman's question also.
Oh, I think so.
I think there's only one choice for the 6J symbol. That's the one I'm using, but there are two choices of the 4-point function. One gives Liouville and the other gives gravity. One choice. Because z to the minus 2 delta isn't equal to z to the minus 1, isn't equal to any other power of z.
It's not another power of the z. It's indeed why it's precisely sort of if you work with integrals that always have densities associated with them, then I think there's only one structure.
I think the Liouville 4-point function. Well, okay, we should talk about that later because I still disagree, but.
Tom, can I try to ask one? So I think the question Nadia's asking, which I think also the question I'm asking, is you have your S channel, which has 5 momenta in it, and you write it as an integral over T channels that have some additional internal momentum added, right? And you want that to be integral dp of the new momentum you're adding, 6J times Cardi, or is the Cardi absorbed into the 6J?
This 6J has a bunch of prefactors compared to that 6J,
Okay,
and so I'm not immediately able to compare them.
Got
It's not just that integrand, you have to put in a bunch of normalization factors. You need that even just to have tetrahedral symmetry. It's not quite the F matrix, it's F times a bunch of normalization factors. So I don't know the general answer to this question of when it makes sense, but the conjecture is that it makes sense when restricted to large triangulations, which are not allowed to have certain types of internal vertices. And in particular, you're not allowed to retriangulate. So you're not allowed to add internal vertices that look like this one, that carve up your tetrahedron into 4 smaller tetrahedron. If you do that, you get infinity, and these amplitudes don't make sense. But the conjecture is that as long as you don't do that, things are well defined. And this conjecture is supported by various explicit examples. Here's an example. So this is one of the simplest graphs, non-trivial graphs that we can consider, the knotted handcuff. Okay, so this is the graph, and we're thinking about this trivalent graph as embedded in S3. What we'd like to do is to calculate the CTV amplitude for this graph. First step is to triangulate this graph in S3. It turns out that this can be triangulated with a single tetrahedron. You have to stare at this picture for some number of minutes to convince yourself that this is true. I can walk you through it after the talk, maybe if you want to go through slowly, but this graph in S3 is the same as this solid tetrahedron with the 2 front faces glued together and the 2 back faces glued together. There are no internal edges in this triangulation. Every edge belongs to the graph. And therefore, the CTV partition function is just the 6J symbol of this single tetrahedron. So this is the answer. It's this 6J symbol for this. Yes?
Is it allowed to take 1, P2, and P3 imaginary to have identity operators instead of some of these lines?
I think the answer is sometimes. But I'm not sure what the restrictions are or when that's allowed.
Did you intend to have three P3s or one of those? Is it supposed to?
There are four
P3s
P3s and there's four P3s. That's intentional.
Okay.
Yeah. That's what allows us to glue that together. Okay, so that's a simple example of how you calculate these partition functions. Now we come to the relationship to Virasoro TQFT. There's a well-known relationship between the ordinary standard Turaev-Viro theory and Chern-Simons, which says that Turaev-Viro is Chern-Simons squared. So we anticipate something similar for our case relating CTV to Virasoro TQFT squared. And it turns out that the relationship between them is a modular S transform. So in our case, these amplitudes are functions of momenta, of Liouville momenta P. And the relationship between, so the relationship is you take your Virasoro TQFT amplitude as a function of P, you square it, and then you do an S transform, which is really just a Fourier transform on all of the momenta P. This S transform of Virasoro TQFT squared gives you the CTV partition.
This for compact groups, or also non-compact?
You mean this one?
I refer to the gay group science.
So this one, I know it's true for compact groups. I'm not sure to what extent this has been defined for non-compact groups. Well, yeah,
That's what you're doing.
that's what I'm doing. That's what I'm essentially doing.
What is the non-compact group in this case?
It's SL2R or SL2C.
You do both.
You mean, is that two different things?
Yeah. But it's quite different if you have SL2C or SL2R.
Yeah, I don't know the answer. I don't know whether you do things. So I want to describe the proof of this identity. This is one of the key results, but the idea of the proof exists already in the literature on standard Turaev-Viro. What one needs to do is to check that define things in a way that makes sense for the Virasoro case, and then to make sure that all the arguments go through even when the total number of states is infinite. It turns out that they do. There's this formalism, this nice formalism called the chainmail formalism that you can use to prove this.
Well, S-matrix is basically going to the dual graph. Is that one way of thinking about it?
Well, it's not a planar graph, so it's not as direct as that, but it's dual in this sense.
That the momentum is flowing in the dual channel.
Yes, that's right. So this picture is supposed to be the triangulation, has edges here. And what this does is it trades the triangulation for its dual spine, which is this graph that kind of goes through in all the dual directions.
In standard Virasoro Turaev-Viro, there's no analog of that Fourier transform.
There is. And this is discussed in this paper of Barrett and collaborators. And the formula, the definitions are a little bit different, normalizations are different, but the formula in the end is the same.
Well, you wrote a formula at the top with no Fourier transform.
Yeah, this Turaev-Viro invariant was generalized to accommodate graphs. And once you accommodate these graphs, you get something that looks the same as the thing in the box, except that it's a sum and it's the S matrix of it's that appropriate S matrix. So if we revisit our example of this handcuff graph, recall that we calculated the CTV partition function, it was just the 6J symbol. You can also calculate the Virasoro TQFT amplitude. It's the modular S matrix with an operator inserted, that's this P3. And the relation between them is the Fourier transform on all of the weights. So take this S matrix squared and Fourier transform all three. you should get the 6J symbol. And indeed, this is an identity that's true that you can also establish directly. So this is how the two theories are related.
So you say again with the S.
Yeah, this is the S matrix for the transformations of the 1-point blocks on the torus. So now we can get back to gravity and discuss how CTV is related to the gravity partition function. So CTV and Virasoro TQFT were both defined for a graph embedded in some closed three-manifold ME. Here's a picture in our example. 3D gravity, you should think of as living on the complement of the thickened graph. So in this case, we have our graph drawn in, maybe this is S3. You thicken out the graph into this solid object. And then gravity lives on the complement M outside the graph. So this M, so we're distinguishing between ME, E for embedding, the place where the graph is embedded, and M, which is the compact manifold where gravity lives. This is a compact manifold with boundary. And we'll impose fixed length or fixed angle boundary conditions on the meridians of the graph, which are the red gammals in the picture. That's where we impose our boundary condition. In this particular example, the outside of this region, the gravity manifold M, is a single generalized tetrahedron of the type that we discussed earlier. So now I can get to the main punchline. Let's start from the fixed length path integral. When we discussed this before, we're called it the fixed length. So the gravity path integral with fixed length was Virasoro TQFT squared. And this is just the usual statement of 3D gravity being two copies of Virasoro TQFT. And I've just restated it in this language of the compact region, fixed length boundary condition. Now we perform the modular S transform, which, when we do this on the right-hand side, transforms Virasoro TQFT squared to the conformal Turaev-Viro theory. On the gravity side, in terms of gravity language, this implements a change of boundary conditions from the fixed length gravitational path integral, this ZL, to the fixed angle gravitational path integral, ZA. And this is just that Fourier transform. Therefore, this topological theory of CTV is really 3D gravity with fixed angle boundary conditions. They're the same. And there's just a translation in from angles to weights that's given here. Yeah, so the weights need to be continued to the imaginary axis to get real angles. Okay. So that's the main punchline about this gravity path integral is that this conformal Turaev-Viro theory is giving you an exact calculation of the path integral with fixed angle boundary conditions. Now with this formula, we can calculate the exact path integral by gluing together a generalized tetrahedra. That's what CTV is doing, is it's decomposing things into tetrahedra. When you fatten out the graph, those become generalized tetrahedra. That does this truncation on the vertices, turns them into generalized tetrahedra. And we can translate calculations in Virasoro TQFT into geometry or into the metric formalism. You can do this for very complicated graphs. So this business of triangulating graphs and three manifolds is probably not familiar to most people. It definitely was not familiar to me before starting this project, but it's very familiar to mathematicians. And there's software. There's even like open source software you can download where you click in what graphs you like, and it tells you how to triangulate it, and tells you all the properties of the triangulation, and calculates its volume and things like that. So this is very well developed. I'll skip this example.
Sorry, could you explain a little more how the Fourier kernel is related to the modular S matrix?
Yeah, the Fourier kernel is the modular S matrix with no insertion. So that's the modular S matrix of the torus character.
But one was a cosine, the other was an exponential, all right?
The amplitudes are invariant under p to minus p, so we can trade the cosines for the exponential.
Thanks.
So I'll wrap up with a couple of comments. This is the most important one. Posit the cosmological constant. There does seem to be a corresponding story in three-dimensional gravity, in three-dimensional de Sitter. And I don't understand this very well yet, but I'll just make a couple of preliminary comments. In fact, the de Sitter case was explored long ago, and a lot of the results that I've described were based on or inspired by this work of Barrett and collaborators, who explored the standard Turaev-Viro theory as a discretized model of three-dimensional gravity with positive cosmological. Their theory has a finite total number of states, and so that might sound familiar to people thinking about de Sitter. It also satisfies an S-transform identity similar to the one in the star. Both of them are related to the quantum group UQSL2, just with a different choice for the representations that appear. There's a difference in the perspective, which is that the perspective in the spin network literature, that is this Barrett and collaborators, is that the triangulation is this microscopic discretized model of gravity. Because they have a finite number of states in their theory, and that it should reproduce Einstein gravity in some kind of continuum.
So they don't have the restriction that they cannot have.
They don't have this restriction on it. And so they allow arbitrary triangulations, which always converge because n is finite. Whereas the perspective that I've taken here suggests another way of thinking about it, where this is not some microscopic triangulation into Planck-sized tetrahedra, but just a decomposition into a decomposition on extremal surfaces.
What is n?
N is the total number of states. So for Virasoro, that would be the integral dp of rho 0 of p, it's infinity. And here it's a finite number. There's a discrete list of states, and n is finite.
But they probably thought it was 1/g or something.
Yes, that's right. Yeah.
There's another way I can phrase it that they don't have problems with the identity assertion. Sorry, I'm just trying to understand Hartman's comment. So in de Sitter, you can insert the identity and there's no divergence.
Yeah, nothing ever diverges in the de Sitter case except because n is finite. Everything's a finite. All these calculations are finite sums, so it's a finite number of states.
But can you calculate the sphere?
I've been trying to understand this literature, and there's very little in the way of comparisons to semi-classics. I haven't found any case where they calculated this and then compared to the on-shell action of something. It may be there, but the language is very different. It'd be a little hard to translate. Yes.
This is SU2 gauge theory.
That's what you meant to say.
Yeah.
Oh, sorry, what's the group? Sorry?
SU2. It's SU2 level K, with 2 copies of SU2 level K.
This actually goes back to Reggie, who related the Einstein action on a tetrahedron to the large J limit of a 6J symbol.
Yeah, so Reggie was using the SU2 6J symbol, and the new ingredient in their work was to use the 6J symbol of the quantum group. So I'll end there just by flashing up some questions. I won't go through all these, but I want to mention one of them, which is the relation to ideal triangulations. So Virasoro TQFT is believed to be equivalent to this Teichmuller TQFT that was formalized by Gaussian and Anderson. This is difficult to prove, but probably true. There's also a Turaev-Viro version of that theory that was constructed by Gaussian, Low, and Vartanov. The difference is a difference between these generalized tetrahedra that I described and triangulating things into ideal tetrahedra. everything in Kashayev-Anderson or Kashayev-Loew-Vartanov is phrased in terms of ideal triangulations. But probably there's some translation between them, and the conjecture is that CTV should be equivalent to their Turaev-Viro theory in the same way that Virasoro TQFT is equivalent to their triangular TQFT. And the other questions I'll just leave you to read, and thank you for your attention.
In the case of standard Turaev-Viro theory, say corresponding to some fixed transimus theory, every gapped boundary condition sort of gives you a way to construct a full consistent CFT built on top of some fixed eligibility parallel algebra. Is there an analogous thing that you can do in this CTV story where boundary conditions of a particular kind sort of tell you how to construct full CFTs on top of Virasoro?
That's a good question. I don't know the answer. I don't know of any way of doing that. Maybe we can talk about it after. Yeah. I don't know whether that would construct individual CFTs. Maybe that's something like an alpha state, or whether it would tell you something about the ensemble of CFTs.
Right.
I don't fully understand why if it was enough to put as boundary conditions, then you fix either the length of geodesics or these angles, where you don't have to, like, say, specify the metric everywhere.
You can specify the metric everywhere. And if you do it that way, then you would say what I'm doing is imposing that there's a hyperbolic metric, like two-dimensional hyperbolic metric, intrinsic metric on the boundary. And I'm just parameterizing hyperbolic metrics by the lengths in those metrics.
It corresponds to the structure constants of CFA. What were the length? You said the length of the boundary cycles.
Those correspond to the weights. So the conformal weight P,
Operators.
yeah, the weights of the three operators correspond to the lengths of the three geodesics.
That's come from some semi-classical.
It does, yeah.
If you, but it's supposed to be exact.
Yeah, the formula in the end is supposed to be exact. However, yeah, it's supposed to, the formula is exact, but I don't know how to do a different gravity calculation where you literally integrate over metrics and get that answer. It's an exact formula that agrees semi-classically with the length.
It's supposed to come from these pieces that were left complex and it grew before, like these asymptotic pieces.
What's supposed to come from it?
So this correspondence that you mentioned is supposed to come from these asymptotic pieces that you were plotting before.
Yeah, if you glue those pieces back on, then everything is consistent. So I would say, not just semi-classically, but exactly. Because we know the exact amplitudes from Virasoro TQFT.
Can you say more about the spin? Seems important to address this question.
Well, I can say more about it in the sense I can explain where I didn't put it in. Okay, so if you work on the Virasoro TQFT side, and then it's easy to put in spin because you have something, Z of P and P bar, and you can just treat P and P bar as two independent numbers. But after you go to CTV, that transform only has one chemical potential per P. So you cannot just you cannot just complexify the angles in order to turn on spin in CTV. That won't work. That would be like, that doesn't turn on independent chemical potentials for P and P bar. So you have to do something more elaborate, and I don't know how to do it. I think a natural way to think about it is by using some technology from BCFT, but I don't know how to do it in any detail. Yeah.
So can you generalize this correspondence of linear function to correspondence of correlation function? So if I put some point operators at this boundary, there's some correlation function that corresponds to some correlation function in the other series.
Yeah, I think, so if you want to calculate, well. This was all a statement about OP statistics. If you want to talk about correlation functions of the dual CFT, then you have to convolve the OP statistics with the conformal blocks. The way that works geometrically is by gluing the core to the asymptotic regions. And you could do that using either CTV or Virasoro TQFT. But so either one can be used to calculate the correlation functions. I'm not sure if those are the correlation functions you had in mind though. Did that answer your question?
I don't know enough.
Okay, maybe we can discuss after then.
So if I have like if I have a Riemann surface, shouldn't I specify like the length of the geodesics and just one the geodesic to fully specify the surface?
Yes, so the full tabular space is 6G minus 6. And just specified half of that. That corresponds to working with scalars as opposed to operators with spin.
But it seems like he has a lot of questions to discuss afterwards. We should release him. Let's thank the speaker again, but before we do that, please send me email if you want to join us for dinner. Please do it by 4 so that I have enough time. Reserve a table.